So I wanted to show you guys, I'm sure, your best friend.
Yes, totally.
The periodic table of elements. Mandla, what can you tell me about the periodic table of elements? Throw something at me. What is the point of this table?
It's a table of elements of energy or sources.
What is an element?
Elements are anything that consists of just go ahead and one.
Sorry? Can I understand? You give a stab at me. You're doing well.
Elements are moving particles.
Good. They're particles. Great. Who else wants to take a stab? What's an element?
It's anything consisting of everything.
Anything consisting of everything. Interesting go. Okay. Felicia?
It's a table that has metal, non-metal, and what's the between what?
Transition metal. Great. Okay. Good. She's learned your terminology. Fantastic. And the section is going to be a lot about terminology. Hunter?
Okay, I'm just trying to think of how I'm going to word this. An element is basically sort of, how do I say it, a pure version of something. Like an element, like say H2O put together as a compound, because that's two elements
Good.
joined together.
I like how you've broken it up. What I'm going to say, guys, is an element falls back to this idea of an atom. An element is a specific version of the atom. The periodic table of elements is essentially saying every single element that's known to us, they've found them all and they've listed them here and they've grouped them into certain groupings that have certain characteristics.
Yes, they are actually more than just that.
They are more than just that. Good. What I want to talk about specifically is we see different types of elements. Okay, some elements are very, very good at conducting electricity, and some elements are very, very bad at conducting electricity. There's also a combination, or we rightly had the correct word, I think, with Felicia, as a compound. Or was it Hunter? Was it Hunter? I'm sorry. Hunter saying there's some compounds that are very good at conducting electricity, and some compounds that are very bad at conducting electricity. So what do we call a substance that is good at conducting electricity? A good conductor, and something that's very bad at conducting electricity?
A poor conductor.
A poor conductor, or an insulator. Good. Thank you, Loretta. Thank you, Ashley. Cool. I want to know, why are metals specifically good at conducting electricity? And some better than others. What does it come down to? What do we say electricity is? Or current electricity is?
I think it's because electrons get to move freely there.
It's because electrons get to move freely. So we want to have a look at what is the bonding structure in these metals that allow electrons to do what we want them to do and move freely, causing electricity. Let's have a look. Now you guys, I'm sure, have heard of 3 different types of bonding. Something called? Covalent bonding. Okay, good. Polar covalent, like polar ionic and a whole bunch of things, but that all, I want to have a look at specifically intramolecular bonding. Okay, hydrogen bonding is intermolecular. Again, a very different topic. I just want to have a look at the 3 different types of intramolecular bonding. Liesel?
I forgot the correct word, but it's the ones that don't have the same valence. The elements that don't have the same valence when they bond. I forgot the
Good.
name.
When they've got a high electronegativity difference, they're producing an ionic bond.
Ionic.
Good.
Yes, that's the
Okay, guys, don't worry if this is all complete Greek to you. I want to specifically focus on something called the metallic bonding, the other type. Okay, essentially those 3 types of bonding are saying what happens between molecules, inside the molecules. How do these atoms bond to each other? And we want to have a picture like this because this is specifically the metallic bonding.
So you forgot the 4th one.
Which one?
Family bonding.
Family bonding. Okay, I forgot family bonding, I'm sorry. What we see here, guys, is the big green circles are essentially the atoms. And specifically in metals, and metals are very brilliant, they conduct electricity very well because of this phenomenon, essentially. These atoms bond together and come closely, but they let their outer shell electrons, so they let the electrons that are furthest away from the nucleus free, just to float around the place. And those are the black dots. So now that these electrons are free just to float around inside the metal, Mandla, what can they do?
They move freely.
they can move freely. So when I give them some energy and tell them to move in a specific direction, what do? They move in that direction. And if I tell them to go through the light bulb, they go through the light bulb, they give the light bulb energy, and the light bulb gets hot and lights up. It's that simple. So what happens is if we zoom in a little bit, we'll see that there are the atom part of it, which is the plus side, and it releases these electrons, or it delocalizes them, and it forms what they call a sea of electrons. So these are all keywords that you can just throw into your exam because teachers love them and they'll give you a tick and you're going to get marks for it. Okay, sea of electrons is a great one. What happens is you get this metallic structure forming, these electrons being delocalized from the atomic kernel, which is essentially just the atom left behind after these electrons have released themselves, and these electrons are now free to move within the metal. Gives it a fantastic property of being able to conduct electricity.
Now, when the electrons are allowed, or they're freed,
Yeah.
are they able to like leave that certain metal, like escape?
Okay, no. So the bonding of the metal itself keeps those electrons within it. And yes, there are examples before I get completely shot down if any of you do want to. The electrons are able to actually leave the metal and go, and it gets horribly complicated. But let's for now assume that the electrons get stuck in the metal, so they're only free to move where the metal dictates it. So if I got my copper wire, they can only move from this end of the copper wire along the copper wire to that end. They can't end up on the roof.
So it's like I have you, but when I let you go, I still have a rope.
It's like we all form a lattice here. Okay, here's an electron. I can pass it to Hunter. He can pass it to Felicia. Felicia can pass it to but it can't go anywhere other than when we're passing it.
Okay.
So that electron is free to move wherever it wants to within this confine. It just can't leave the confine of us. Sorry?
Kind of like us at dream school.
So you guys are dream school, exactly. All right.
Here, just not.
Okay, guys, so that's the idea. But what we want to move on to is, again, taking our step completely back. We don't want to think about the atomic level. We don't want to really mind about a little bit what's happening with the electrons. We don't really mind what's happening with the protons. We're having a look at what's happening when we try and move electrons from point A to point B. How can we do this?
An electromagnetic field.
Okay. Electromagnetic field. Yes, we're not going to talk about that either today. So you can see this topic is really huge, and we can discuss it in serious depth and spend actually the next month in it. I'm trying to focus it down as much as I can to explain to you guys most basically how we can piece together that corner. That's my thinking here. Okay. The very first thing that we need. What do we say the most important components of a circuit are right at the beginning? Sorry. Conductor. We got a conductor. Fantastic. Victor? So what are our three things that we said we needed in our circuit for it to work? Right at the beginning. When you're talking about energy.
It's circuits.
Good. So we need the circuit, which is the conductor.
Yes.
Fantastic. Okay. With you, Ashley.
An energy point naming a cell.
An energy source. Something supplying the energy. Great. For our terms, what did we say that energy source was? I think Loretta had it.
What about a switch?
Sorry?
What about a switch?
We'll come to a switch now. Okay? A battery. Fantastic. Thank you, Jackie. A battery. Battery cell. For today, let's call it the same thing. That cell has energy. We quantify that energy with something called electromotive force. Okay? EMF. Electromotive force. That is the we quantify how much energy this little cell has. How much does it want to push electrons from point A to point B? Kind of with me. Liesel.
Hello.
You need a load. Fantastic. Okay, I think that one's not coming up next. I put conductors next, but you're absolutely right. We need a load. What happens is we got the source of energy. It's passing the energy to the load of energy, something that's using energy, a resistor in this case, and it's moving. It's doing that by using electrons to pass the energy around the circuit. So it has to be connected in the circuit. Now, we could break the circuit, technically. If it's not connected, can the electrons then get around the circuit?
No.
They can't, okay? So what we talk about in electrical circuits is something called a closed circuit. If we close the door, can you typically get through it?
No.
No, all right.
Except
So,
if you're a ghost.
sorry?
Except
Except if you're a ghost, yes. Giovanni, thank you for that. Guys, so can you see that this terminology is slightly not intuitive? Closing a circuit means that we're actually turning it on.
Yes.
Yeah.
Because we're allowing those circuits, the electrons to flow, because we're completing the circuit. So I much prefer the terminology completing the circuit versus closing the circuit, but you will often have the question, what happens when you close the circuit? Think about it, you're connecting the pieces together and you're allowing electrons to flow.
So basically it's like something like this and then
What we'll see here, and I think Lorato had it, is we have a switch to allow us to close the circuit or open the circuit to stop the electrons to flowing. Cool.
I've got a question.
Yeah.
When we close it, it goes through, right?
Good.
But doesn't it make more voltages, which would make it go
Okay.
and then overheat?
What do you mean by voltages?
I mean like the electrodes.
Okay, more electrons.
Yes.
Cool. Now, this topic is going to get quite convoluted. And the first thing I want you to notice, and Lisa's got a very confused face, so I'm glad why. What is your confused face?
Who's gonna ask my question?
I don't have, I'm not confused.
You're staring at the board.
It's distracting.
He's fascinated by the movie.
Okay, what is disturbing you on the board?
Those moving electrons.
Okay, are those electrons? What do we say electrons are?
Those are negative cells.
Electrons are negative. What is that?
That is
Those are,
protons.
okay, but protons don't move. Remember, if we think about how our actual,
Those are volts.
those aren't volts. Okay, so what we've seen there is little positive charges moving around the circuit. Now, what happens, and I'm afraid I can't give you a better explanation of this because it just doesn't exist. When electricity was first kind of discovered and we first started playing for it, we didn't really understand how it worked, okay? So it made sense for us to assume that charges moved from the positive side of things to the negative side. You guys happy with that?
Yes.
It made sense for us to think of it that way. So what happened is we started defining current as the flow of charges moving from the positive side to the negative side.
I see.
Whenever you think of electronics, which is absolutely bizarre, you actually think of it as the flow of current of charges from the positive side to the negative side. That is called conventional current. Unfortunately, you guys know that's not actually how things work. How do things actually work?
In what way do you mean?
Do those positive things move? Those positive guys don't move. Sorry. So I had a big conventional current there, okay? Those positive guys don't move. What actually does move
Is the electrons.
is the electrons. The electrons all move and carry the charge. So that is actually supposedly, well, actually from the negative side to the positive side, that's called electron current, okay? That's,
Sun doesn't really begin from.
it actually begins from the negative side. Good question. But whenever we analyze the circuit, it doesn't really matter. The fact of the matter, if the circuit's not connected or not closed, it's not completed. We can't analyze it. Okay? And whether they go from the positive side to the negative side, we actually don't care. As long as we are correct in what we are saying. So,
How did you determine that?
sorry,
Life
what?
is a lie.
That they flow from the negative to the positive?
Good. How did we determine that? We go back and we have a look at the model here. Can these guys move? Can you see they are locked in space? They can't move. What can move?
The electrons.
So what must be moving?
The electrons.
But you see, that understanding only came way later. So when they first started understanding this kind of theory, they said, well, let's assume the current flows from positive to negative and call it conventional current. It's essentially out there to confuse you guys. Okay, I'm joking, but okay, but it's really not that bad. All you guys need to make sure that you understand the difference is, let's essentially for the future assume that current flows from positive to negative. It's nice to think of it that way. Let's just assume it does that, except when you ask specifically, what are the electrons doing? What is the electron current doing? And then you can answer what? What? What are the electrons doing? The electrons? But they're loose and they're able to move, so as soon as you provide the energy, what happens?
Oh, well, they
Mandela has it at the back. What do the electrons do? They move. Fantastic, okay? The electrons move. So the electrons are the ones that move, okay? It's that simple.